Hi everyone and welcome to the presentation. My name is Will Harris. I work in global business development and marketing for KMLabs. The title of today's talk is Small and Fast, and I'm really referring here of course to two sort of coupled phenomenon in the physical materials world where we're going to be looking at very small things and very fast things, and of course these tend to happen hand in hand. And so we're going to talk about how this spatio-temporal coupling of phenomenon can be nicely observed with some emerging techniques in the sort of vacuum ultraviolet to extreme ultraviolet and soft X-ray range. And principally the tool that we're going to discuss that's now capable to do this is the KMLabs Quantum Microscope. So this is a new instrument concept that's based on an imaging modality as well as a variety of different spectroscopy and analysis modalities available as well that together let us reach a broad variety of applications in the nano and quantum space. But just to give a quick history for those of you not familiar with the company, KMLabs has been around for about 25 years as a spin-off company from the University of Colorado at Boulder and the renowned JILA lab, known for advancements in ultra-fast laser science. So the company initially started as designing and building laser kits, and then eventually full laser sources, and more recently evolving to not only light sources themselves, but full integrated instruments, really considering from the light source all the way down to an experimental station. And that's kind of the theme that we're going to pull on today, which is looking at what can we do when these types of light sources actually interact with materials, what kind of signals can we create, and how can we use this to do some interesting new types of science. First, it helps maybe to give a little bit of overview for those of you who haven't used any of these types of techniques in the past. I've shown here, this is just a simple cartoon schematic of a sample that happens to have two layers to it, so material A, material B. You can see on material A there's some amount of heterogeneity represented there and some graded composition or chemical information that's contained across the surface, just meant to represent a non-homogeneous sample. So we can impinge a laser on the surface of the sample. So this is the incident beam characterized by some wavelength, some intensity E, and some phase of that light phi. And we do this at some incident angle theta. And of course, when we shine light on a surface, a few different things can happen. We can have light that's reflected or diffracted off that surface, and we can collect that diffraction pattern. And ultimately, that light is containing, again, wavelength information, some attenuated amplitude, and maybe some phase shift within it. Depending on the thickness of the sample, we might also have transmitted light, so that's shown on the bottom of the figure here. So some amount of attenuation as it passes through the sample. And we may have photo emission processes as well, where exciting electron transitions and then getting emitted electrons that we can then collect and use as a spectroscopic probe. We can introduce now multiple lasers into the system as well to start to look at dynamic type of effects, and if we sync up or coordinate the timing of these two lasers, we can start to look at some interesting things. And the example I've shown here is using what we'll call a pump laser. So this is used to pump some energy into our system, and this can be realized in a number of forms. So we can introduce some mechanical vibration, essentially some mechanical and thermal energy. Eventually this vibrational activity will be diffused out into the lattice, and we'll have phonon transport or essentially heat transfer processes occurring on the quantum and nano scale to dissipate that heat as the system relaxes back to equilibrium. And if we have something like a magnetic sample, we can also alter spin states by means of a pump laser. So there's a variety of different types of interesting phenomenon here that we can potentially observe. It's just a matter of what technique are we going to use for what type of application. So we'll get into that here. And I've kind of taken what I showed on the previous slide and grouped it into three different topics here. And I'm calling this really a revolution in the lab and applications that we can do with ultra-fast and short wavelength laser sources. So these are techniques that have not been traditionally commercially available, somewhat accessible to kind of the specialized laser optics lab or the synchrotron community, but really without a broad reach. And that's what we're trying to change here with this new commercially supported system. So we can look at it in terms of imaging modalities. So that's shown on the left here with coherent diffraction imaging. So this is a methodology for doing surface and near surface imaging of chemical composition, elemental structure, topographical information, getting some depth profiling, and so on. On the top right, I've showed spectroscopy, and the diagram here is depicting angle-resolved photoemission spectroscopy, or ARPES. But more generally, we can imagine doing a variety of different types of spectroscopic measurements whenever excitation in, say, the 10 to a few hundred EV range provides a meaningful transition or information that we might want to look at. And on the bottom right, as I had mentioned earlier, we can look at ultrafast dynamics now as well, and this is typically done by syncing up multiple laser pulses in what's called a pump-probe arrangement, where we pump some energy into a system to induce a transient state, and then we probe it at different time delays to watch that state as it evolves and eventually makes its way back to its equilibrium condition. So there's a whole bunch of things captured within here, and kind of the overarching theme here is we're trying to approach this from a perspective of a multi-purpose tool with different modalities serving slightly different application and research interests, but all kind of under this umbrella of nano and quantum science, and looking at the phenomenon and dynamics that occur at both those length and time scales, and learning about the fundamental processes that will ultimately impact device design and future engineering. So this idea of a common light source that serves multiple experimental stations is actually a familiar one. If anyone has any experience in the synchrotron community, this is basically the model that these sources follow, where you have a common light source and multiple experimental beamlines that branch off it, each of which leads eventually to one, or in some cases even multiple experiments per beamline. And of course, synchrotrons can cover typically a pretty broad range of photon energies and have plenty of flux. It's one of or a couple of the strengths of the system. But it turns out we can actually leverage a kind of similar instrument model in the laboratory, where we're taking a coherent laser-based light source, and we can feed that into multiple experimental chambers, maybe in some cases at the same time, but even just switching between multiple different chambers. It makes sense from both a logistical perspective of having a common light source that's occupying some space and building up a lab around that expertise. Well, we might as well serve multiple experimental interests. And it makes financial sense as well, of course. There's a lot of shared equipment between these different setups, whether you're doing imaging or spectroscopy or pump probe dynamics. So we might as well take advantage of this and be able to set up multiple experimental stations that we can switch between. So very much kind of the same theme. And there's actually similar things that happen in other experimental techniques as well, taking, let's say, electron microscopy as an example, where an SEM or a TEM is principally an imaging method, but you can apply all kinds of additional modalities and detectors onto the system as well. So I mentioned we're operating in the vacuum ultraviolet to EUV and soft X-ray range, and so that begs the question of what's attractive about this part of the spectrum. Well, I plotted it across the bottom here, at least a portion of the electromagnetic spectrum, and the blue oval kind of depicts roughly the range there that we're working in. And what I showed on the top left here, I took the periodic table and I looked for where we have absorption edges, namely KL or M edges of different elements that fall in this range. And you can see them, they're color-coded, but it covers quite a bit of the periodic table, a lot of the important elements that we work with in chemistry or engineering or material science. And of course, if we can access the edges, that's really attractive because the edges principally serve as a source of contrast for those elements or chemical compounds that involve those elements. So if we can access the edges, then it means that we can maybe do some unique things to study those elements. One such example is shown here, just taking elemental silicon as sort of a simple example, has an L edge just under 100 EV, which is depicted here. And silicon, of course, with a lot of relevance to the semiconductor and nanoelectronics community. But we can see similar kind of edge effects for a lot of these different elements shown. And maybe not all under the same configuration, let's say. Maybe not all with the exact same microscope. But the user has, of course, some flexibility now to choose what elements and what types of experiments are most important, and then we can design an instrument that's going to be able to fit those needs. Another way of looking at this, I actually come from a background in the microscopy world, both academically and earlier in my professional career. So one of the things we're going to do with this type of light is we're going to use it as an imaging probe. And so it's useful then if you come from a microscopy perspective to look at how we fit in with the other techniques that are available. And of course, the obvious one is to start with optical or visible light microscopy. Very robust and routine technique, been around for a couple hundred years, and in some of the most advanced, say, confocal or super resolution techniques, we can get a couple hundred nanometer kind of length scale, at least that order of magnitude. And if we jump way over to the right end of the spectrum, also looking at photons, we can do hard X-ray imaging in the lab or at the synchrotron for that matter. Lab-based hard X-ray sources using essentially the Röntgen tube design are ubiquitous these days and can be used for things like hard X-ray tomography, looking at relatively large objects. And of course, we can't leave off electron microscopy from this picture. SEM and TEM, known for especially high resolution, sub-nanometer, and in some cases for the latest TEMs, well into the sub-nanometer regime. And as I mentioned earlier, we can add additional detectors and modalities onto them as well. But what we notice, of course, is this big gap in the middle here, this VUV to soft X-ray kind of range, where there's not a whole lot of imaging work being done to date. And what we'll see is that it's just starting to come into its own now, and it's very much analogous to the early days of these other techniques where the microscopes initially are sort of the scientific experiment themselves, right? The research is based around just getting the microscope to function, seeing what kind of data you can extract and how far you can kind of push the performance of the system. But then over time, things segue to where the emphasis is not on instrument design anymore, but it's actually on an application, right? What meaningful information can we extract when we put a sample in there and we actually image it and we learn something about it? And we're just on the cusp of this transition now when we talk about this intermediate, EUV kind of length scale imaging. And what's super attractive about it is we now have laboratory sources. Well, that's very good. We didn't have those up until relatively recently. They operate at short wavelengths, so kind of tens of nanometers. And when we image without lenses, we can get rid of aberrations and degradations that are associated with imperfect lenses. So we can get resolution that's kind of on the same order as that wavelength of light. We can do it with little or in many cases no sample prep. We can get really nice compositional and elemental sensitivity for the reasons I discussed on the previous slide. We can get topographic information and look a little bit into the subsurface and see buried layers and so on. So we get some nice capabilities that really complement the other tools in our microscopy toolkit. And how do we actually do this? Well, we're going to use a technique called coherent diffraction imaging, where we shine a laser beam onto a sample. A diffraction pattern is reflected off of that surface, and we can image that diffraction pattern. And then we raster the beam across the sample with slightly overlapping spots, and we collect many of these diffraction patterns, tens of them, up to maybe hundreds of them. And then we can use a computer algorithm that will reconstruct these diffraction patterns back into the real space, right? The diffraction basically represents a Fourier transform of the frequencies on the surface of the sample. And when we reconstruct that, we can then bring it back into the real space and get what we're expecting more intuitively, an actual image of the features on the sample. And as I mentioned, because we're not using a lens here, you notice there's no lens between the sample and the detector. We can get essentially wavelength limited resolution or diffraction limited resolution. So we're going to be able to get spatial resolving power that's more or less equal to the wavelength of the light. In some cases, maybe even a little bit better. This is an example, one result using this CDI imaging technique, and I'm drawing a comparison here actually to SEM just to get a little bit of a sense of the relative capabilities. The SEM images are shown on the top left. What we're looking at here are titanium patterns put down on a silicon substrate, and clearly then there's also some other compositional variations going on. But we can see that the SEM on the top left, reflection mode CDI, as I had just described on the last slide, shown on the bottom left. And you can see, of course, we can see the same features. And in some cases, we even get much better contrast of some of these subtle compositional variations, or what's probably sort of foreign particles or foreign elements that have been deposited on the surface of our sample at some point during the prep or transportation process. And shown on the right is actually what we're really getting from CDI. We get two images, or two maps, so to speak. And this is because we're dealing with a complex electromagnetic wave that has both an amplitude component and a phase component. And when we go through this reconstruction process, we get a map of each. Right? So we get a relative amplitude across the surface and a relative phase shift of that light. And encoded in these is information about both the composition and the height, or the topography of that surface. And principally the composition comes mainly from amplitude information, and topography largely from the phase shift information. So just as a summary, to give kind of the bullet points of what we're doing with CDI, we get both this reflected amplitude and phase. It gives us really nice sensitivity to composition. Remember, we saw those elemental absorption edges on the periodic table I showed earlier. And if we can image in the vicinity of edges, we're going to get really nice sensitivity to the chemistry. And this is especially true for low Z elements. And that's a place where something like electron microscopy kind of classically suffers when you get down to the less than 5 or 10 atomic number. And as I mentioned, we're going to get resolution on the order of the wavelength of light, so around 10 nanometers or so. We can do imaging across tens of microns field of view and acquisition in a matter of minutes. And of course, then there's some reconstruction and processing that comes after that, and depending what you want to do with your data, there can be substantial processing. But that's really, similarly the case with other microscopy or experimental techniques as well. So I mentioned we can, to some degree, see the subsurface and see buried features. And I wanted to give this quick example looking at, again, a pattern structure that's shown in the middle of the slide here. So this numbered pattern put down on a substrate. And this was then coated with 100 nanometers of aluminum. And when you do that and then you look at it in an optical microscope, of course, the pattern is completely gone, right? All you see is the surface of the aluminum. When you look at it with AFM, a little bit further to the right, you can see that in the uncoated case, we see this pattern pretty clearly. And even with the coated case, there's some amount of topography that is sort of propagating its way up through that coating layer. And so we still have some resolving power with AFM in this case. The power of CDI is that, well, depending on the elemental composition of that coating layer, we'll be able to see typically tens of nanometers, or in some cases a few hundred nanometers down beneath the surface, and see really clearly the types of effects that are happening there. And so what we can see here is this 725 pattern quite clearly in both the uncoated and coated case. And we actually note there's a contrast inversion here of those numbers relative to the substrate behind them. And this is indicative actually of some sort of interdiffusion or interlayer formation, where we're probably getting some reaction products that are forming at the interface of the different chemical layers here, and coupling this with some modeling of the reflection process, we can maybe even tease out what kinds of chemical compounds or interfaces we're starting to form. And one more example, so to look back again at this idea of imaging around absorption edges, we can take lithium, of course a low atomic number element, as a nice example, and lithium, the obvious relevance today is lithium-ion batteries, both a ubiquitous technology as well as quite a strong research topic to see how we can further improve that technology. One of the things that happens in lithium-ion batteries is that as they go through their cycling, electrodes and electrolytes tend to react, and you get lithium forming with all kinds of other elements that exist within that mixture to produce different compounds. Some of which are okay and some of which are detrimental to the battery performance. And they'll give a little bit different absorption spectra or behavior around that lithium edge, which is what's shown on the right here. And one of the nice things about the quantum microscope and the lab-based sources is that we have the ability to access this edge now in the laboratory and So we have some ability to map out these different compositional structures spatially and quantitatively across a sample. And this gives us really nice sensitivity that would be probably pretty difficult to achieve with any kind of other typical microscopy technique. There's also potentially some applications in the biological world as well. Everything I showed so far was materials, sciences, or engineering of some type. But we can potentially do some things in life sciences. It's quite early days here. There's been some early work out of the University of Southampton, which is actually the example I'm showing on the right here, comparing hard X-ray tychography done at a synchrotron with EUV tychography that was done on a lab-based source, and notably avoiding some of the sample damage issues that tend to plague biological samples in the hard X-ray range. But with EUV, we can potentially image fine neural structures at high resolution, and we can do this with unstained samples. So there's some attractive aspects here for the biological world, but again, it's somewhat early, and the future of this technique, and really where the strengths lie, has some room for exploration. So I would say those eager to develop and look into the possibility of a new microscopy modality may want to consider this. So small and fast, that was my title. If you remember back to the beginning, I said this presentation is going to be about small things and fast things, and in fact how those two are related to one another. So far I've showed a lot of small things, kind of nanometer scale stuff, but what about the really fast things, you might ask? I haven't really touched so much on that yet. But it turns out, of course, that the small and fast things tend to be coupled. That the smaller features and smaller length scales we talk about in the physical world, the relevant dynamics and transient states there tend to happen quicker and quicker. So on this simple plot, I pulled this from Professor Murnane from University of Colorado Boulder. So she's plotted a number of different physical phenomenon, both in terms of their length scales and characteristic time scales. And you notice as you go up towards the top right, we get smaller things that tend to happen faster. So charge dynamics, spin dynamics and spin transfer types of phenomenon, phonon transfer and so on, where we're down on the nanometer, or some cases even less than nanometer length scale, and we get things that happen on the pico and femtosecond time scale. So these are inherently linked, right? So we want to leverage the fact that we have a laser source that is both short wavelength, giving us the spatial resolution, and pulsed femtosecond pulses, which will give us the time resolution. So that's great because it lets us start to interrogate the coupling of these phenomenon in detail. I mentioned earlier this idea of pump probe measurements. So for those of you not familiar, I'm going to give a little bit of background here of what that looks like. It sometimes goes by different terminologies, so people say pump probe measurements or dynamic spectroscopy or time-resolved spectroscopy. These kind of refer to the same general class of techniques. And the idea is the following. We're going to pump some energy into our sample. It's going to induce a transient state, and then we're going to follow that a short time later with a probe, which is essentially some kind of measurement of the sample very quickly. And then very soon thereafter, the sample relaxes and it gets back to equilibrium and it's right back where it started. And then we're going to do that same process again at a slightly different time delay and rinse and repeat over and over until we build up an idea of the dynamics. So I'm depicting that here with multiple iterations of pump and probe. Again, the sample returning to equilibrium between each one of these iterations. And we can do this many, many times and take many measurements using that probe, and I've shown just 5 of them here. But we can imagine extending this to many, many more measurements, and we ultimately build up a pretty good depiction of the phenomenon dynamics that might evolve over the femto to pico or maybe nanosecond kind of time scale. And this can tell us about what's actually going on in the material. So there's a few requirements we can imagine that we need in order to do this type of experiment. Of course, those pulses need to be basically instantaneous relative to the event. So they need to be very, very short pulses compared to whatever dynamics we're observing. And you can think about photography. You need a really quick shutter speed to capture, say, athletic photography or sports photography where things are happening really quickly. The pump, of course, needs to serve to provide input energy to produce whatever kind of the desired excitation is, and we'll look at a few of them in the following slides. The probe follows at different known time delays and makes some measurement of that phenomenon, ideally without modifying or actually impacting it, so it's a purely sort of passive measurement. And that probe needs to have sensitivity to whatever dynamic phenomenon it is that we're trying to address, right? So there's different types of probe measurements that we can make depending on the experiment. And again, we'll see some of them. And the nice thing about all this is that the time resolution isn't limited by the detector, which is good because we don't have detectors that can go at the femtosecond or picosecond rate, but it's limited by the duration and the quality of the pulses. And that's also good because we can get quite short pulses of very high quality. Let's look now at some of the things we can do with pump probe. And I'm going to jump through a few different types of phenomenon that we may be interested in, and starting with thermal transport, and namely thermal transport in nanostructures. And the obvious relevance here is in the nanoelectronics world, where, of course, we all know Moore's law, where we'll get more and more devices or more and more elements, transistors on electronic devices over time. And as things get smaller and smaller, they tend to generate a lot of heat. And this can become a problem because now you have heat management concerns. You don't want your material going through frequent and radical thermal cycling over and over again. It's just going to lead to fatigue and failure. So in this simple case, we have nickel lines that have been patterned on the surface of this substrate. And there's many of these lines, but just two of them are depicted here. And we hit those with a pump. And when we pump some energy in there, the nickel heats up really quickly. It expands, it causes some vibration of the material, and then it also starts to diffuse heat into the surrounding substrate by way of phonon transport. And it turns out that phonon transport effect is really dictated by a few different length scales, and that is the size of the heat sources, the spacing in between them, and then some characteristic mean-free paths of the phonons themselves. And so we can do this kind of pump probe scheme where we're pumping in energy, and then we're doing a probe measurement that's essentially measuring the vibrational position of those nickel wires. And we can watch that vibration essentially ring down and make its way back to equilibrium. And the rate at which that's decaying, which is what's shown by the green line here, is essentially representing the rate of thermal diffusion effects of those phonons moving away from the nickel. And this can tell us a lot about the nanoscale thermal transport and how it's coupled to the length scale of these types of structures. And interestingly, one of the key findings that came out of this particular study was that rather counterintuitively, very small heat sources are actually found to create more efficient heat diffusion than their larger counterparts. So this goes kind of opposite to what we would expect, where we would think as things get smaller and smaller, heat management problems become more and more severe. But the researchers actually found that there's a threshold where once these things get small enough and close enough together, the phonons start to interact with one another from the different heat sources and actually contribute to the efficiency of that heat transfer process. So that's a pretty interesting finding if we want to keep designing smaller and smaller heat-producing structures. So I mentioned on the previous slide that when we injected heat with a pump, we caused some vibration of our sample. So what can we learn from that vibration? And that's the question that we're answering here, where again we've put a grading down on the sample, and in this case we've got a thin film. And this could be a few nanometers, 10 nanometer, a few tens of nanometer kind of thin film. And we really want to learn something about the mechanical properties or the physical properties of that sample. And so we can follow a similar type of pump probe arrangement. And what's shown here on this graph is a similar type of vibrational behavior and decay back down to equilibrium. So this is kind of a similar type of effect that we saw previously. But if we zoom in at the very early stages of this process, the first kind of few picoseconds, which is what's shown by this highlighted blue region to the far left of that plot there, is we get some other characteristic vibrations that happen very rapidly and very early on in the process. And it turns out these are longitudinal acoustic waves that can be attributed to acoustic wave vibration basically bouncing down through the nickel grating, through the thin film, off the substrate and back up. And when we analyze the frequency of these oscillations, it can tell us about the mechanics going on within both the grating and the thin film. And coupling this to some modeling, the researchers found that they could extract things like the Young's modulus and the Poisson ratio of that film and plot the relationship between the two and actually see some interesting behavior depending on the composition of that film. But what's really remarkable here is that we can do this for films and structures that are even down to the nanometer length scale. And this is pretty important because when we're designing these kinds of nanomaterials, our classical physical characterization experimental tools don't really apply. They have certain assumptions or capabilities built in that dictate they need some amount of length scale or some amount of material to produce a reliable reading. But once you get down to these tiny length scales, that just doesn't hold. And so now this is really useful where we can use an optical technique and we can be able to probe these types of effects leveraging the optical and mechanical interactions of that beam with the sample. And we can do it on really, really small things that aren't possible any other way. One more example of the pump probe is to look at magnetics or spin behavior in materials. And it turns out for magnetic materials like iron or nickel or cobalt, when you hit them with a pump laser of the right wavelength and energy, an interesting series of events can unfold on the femto to pico and nanosecond time scale that include electron thermalization, a demagnetization step, and then eventually the diffusion of that heat into the surrounding lattice as the system relaxes. And what's interesting about this is that the exact nature and timescales involved in this process are still somewhat of a matter of debate and really not very well understood. And we can start to understand them using this pump probe methodology, where we can use a probe beam that will give us sensitivity to spin states in particular elements. And that's what's shown on the bottom here, where we're looking at the magnetic spin states of, in this case, nickel and iron, shown by the blue and red arrows. And we can probe those at different time delays to watch how those spin states change over time. And we're actually doing this as sort of a side comment here. We're doing this using a technique called MOC spectroscopy, or magneto-optical Kerr effect, that's based on the idea of when you have a magnetic sample, the intensity of a reflected beam off the surface is going to change as a function of the magnetic spin state. So we can leverage this to make this kind of MOC measurement over a series of time here following the pump and back out essentially the magnetic dynamics occurring in each of these elements. And there's a nice application of that. This was published by Gilla a couple years ago. And the idea here in the application is really looking at spintronic devices, right? If we want to move away gradually from electronic devices where we have charge transfer processes that are inherently lossy and they generate a lot of heat, we can move to something like spintronics, which is much more efficient and potentially much faster. But we really then need to understand the fundamental processes occurring, dictating the spin behavior of domains down at the nanometer scale. And the study that was done here was, again, using the nickel and iron systems, placing them in very close proximity to one another with different separators. So in the far left case, we have a conducting separator. In the middle case, we have a scattering tungsten layer. And on the far right, we have a silicon nitride insulator. And so what we can do here is we can pump some energy into the system and watch how the spin states of nickel and iron evolve over time and try to understand how or if they're interacting with one another. And what we can pretty clearly see in the plots on the bottom is that we do in fact get very different dynamics depending on what that interlayer is. In the far left, we get an increase in the iron magnetization while the nickel decreases pretty substantially, while in the other two, we get a similar demagnetization of the nickel, but it sort of pulls or drags the iron down with it, so to speak, where we have a lesser magnitude demagnetization of the iron as well. So this tells us there's some amount of spin transport or spin coupling effects that are happening between these nickel and iron layers, even with different types of insulators or scattering layers between them. So we kind of really want to understand this, because if we're ever going to build nanoscale devices based on spin as a means of data storage, we better understand how that's affected by the local structure and chemistry surrounding that spin storage media. And that brings us to a summary here at the end. We've talked through a number of these different techniques, although certainly not all of them. But again, coming back to the concept of a common light source in what I would call a traditionally difficult to access part of the electromagnetic spectrum, finally coming of age in the laboratory, where we're moving out of the realm of this vacuum ultraviolet, extreme ultraviolet, and soft X-ray light that was previously just the domain of some very specialized laser physics labs worldwide. And we're now on the cusp of it becoming a much more routine and accessible light source for experiments serving a variety of different scientific topics. And this ranges from imaging to complement what we already have in terms of visible light microscopy and electron microscopy and AFM, but we're adding some new contrast and new sensitivity to it. We're doing some interesting things in spectroscopy, where we have very strong interactions of photons with material in this energy range. Remember, think back to that periodic table I showed again, where we have a lot of edges and a lot of interesting chemistry that we can probe in the tens to few hundred kind of EV range. And because we're using an ultra-fast pulsed laser source, we can really look at the dynamic effects dictating the behavior of materials on very, very small nano and quantum length scales. So we can look at chemical or electronic or magnetic or thermal or even mechanical property type of effects down at these length scales that are really tough to see any other way. So with that, I want to thank you for joining us here. This is my contact information. Again, my name is Will. You can always reach out to me with the email below. And we're happy to chat and really dig into any of these applications farther and explore where the interests might be. So thank you for tuning in, and talk to you next time.